Have a great day. You're on the board, Josh? Did you write it on the board? Yeah. Okay, sorry, I just can't see it. Okay, so for here, I'll just sit close to you so you yell. Okay, so for our last section here, this is kind of just like a wrap up of all of our topics. So I'm going to do just a quick recap of all the formulas that you need to be familiar with. More or less, they're all the formulas that are on your formula sheet there. So you need to know how to do like the V equals D over T formula, velocity is distance over time, or speed is distance over time. There's also one that goes like acceleration is velocity final minus velocity initial over time. I think those ones are like right next to each other in the book. And then if you drop down a ways, there's one where it's like D equals like it's VF plus VI over 2 times T. There's that one. And then there's one that goes D equals VI squared plus 1/2 AT squared. Those are, I think, the main formulas we started with, where these ones all involve distance, time, velocity final, or velocity initial, or acceleration. So that was kind of lesson topic 1. Topic 2. Topic 2, then we would talk more about, like, say, forces, things along those lines. So one of the main formulas was that force is equal to mass times acceleration. That was one of the main ones. There was another one on our formula sheet that went like your net force is equal to like your applied force plus friction. That was on our quiz the other day. We didn't use that one. I had to make sure the directions right. I'm trying to think what else we did. Then the third topic, we talked about something called momentum and impulse. And there's a couple ways of writing that. One of the ways to write impulse is F times delta t. Another way of writing it is as like a change in momentum, which is like your change in mass. What's it? It's like a change in the mass, or it's like your mass times the change in your velocity. There was a question on your test about which one of those was impulse. Maybe I should Okay, well, maybe I'll answer this one here. It was like the change in momentum is also equal to like PF minus PI. So, yeah, it literally says it right in the data booklet. So hopefully this is the way, but like one of the answers is this one here. FW was a momentum one, and the other one was the PF minus PI. That was another one. The other two looked really close, but there was something wrong with them. That one gets rearranged as F equals M VF minus VI over change in time. That one was actually on the quiz like 2 or 3 of the times. So. Yeah, that formation actually reminded me of what else I've missed. It's actually covered most of them now. So let's see, this one, that one. Where's the force line? Okay. We don't, for whatever reason, seem to do anything with work and power in this course. So I'm guessing.
Bailey Davis, can you please come to the office for checkout? Bailey Davis, please come to the office for checkout.
And I talked about these ones, and these ones here. Okay. So today what we have to do, if you guys can see the formula sheet, I'm going to cover 2 more formulas down here at the bottom, which are potential energy and kinetic energy. And you probably remember them from science 10. Here's a probably these formulas. And then we're going to talk about certain types of collisions, and we'll talk about these formulas here. And that more or less covers this whole section. And I would say that, like when you guys are writing your test, it's probably about even half and half, where like half of your questions were like math type questions where you had to use numbers and formulas. And the other half were like theory, kind of think about kind of questions. So that's not about like what else there. So, anyways, we'll look over your quiz. Okay, let's do this last thing also. So, what we need to talk about today is what's called conservation of momentum. The idea is back in Newton's first law. And you guys remember what Newton's first law is? Like looking at it being read there? Yeah, basically stuff stays moving or doesn't. This pen is not going to randomly start moving. Right? And once I throw it, it stays moving until something stops it. As soon as it hits the ground, well, then it stops. So, we talked a little bit about the concept of impulse then. The force that stops the object applies an impulse. the impulse goes the other direction, by the way, right? We talked about this when I was with the freshman year, right? The idea that if you have a clay ball that hits the wall's impulse is actually hitting it back the other way. So we want to talk about anything that involves a collision. And so there are no, not on the slide yet here. I pulled this from my physics 30 class. I don't think you probably need to worry about it too much, but do you guys know the term isolated system? You've heard it more than that. Okay, over off the side there's three different kinds of systems. There's what's known as an open, a closed, and an isolated system. An open system basically means stuff comes in and out all the time. Like if you think of our classroom, the door is open right now, so Emily can just walk in our classroom. It's an open system. Okay. If I want to make it a closed system, I close the door, and then people can't just randomly walk inside. Okay. In terms of like chemistry and physics, usually a closed system means you put a lid on something, and that stuff can't somehow escape. A true isolated system means that not only can like stuff not escape, but like energy should be able to escape either. So like you should never have a loss of energy. That is usually almost impossible to have happen in real life because really there's always a loss of energy to something. But assuming that more or less it's considered to be isolated where there's no loss of energy, we have what's known as the momentum conservation formula, where basically whatever momentum you had after a crash should be the same as whatever momentum you had before the crash. So, I threw this in my physics 30s. There's a picture here of a cannon on like a super old one of those like pirates that were used to shoot ships here. There's a rope. It's ever so something back. Let's see what that rope is. Why do we need a rope? It's not the fuse for the cannon. What happens when you shoot the cannon? Well, the cannonball goes this way. You guys know that the cannon itself actually would rock backwards towards you? You guys ever heard or seen that, or you guys ever shoot guns? Fire guns? What happens when you fire a gun and the bullet goes this way? Yeah, we call it like a recoil, right? This is a good example of conservation. If something gets shot that way, well, in order for it to be conserved, something else must go the opposite way. That's Newton's third law, right? We even talk about that like the propeller concept. The reason why a boat goes forwards is because the propeller pushes water backwards. So anything that involves some sort of like collision or explosion, we have to conserve momentum. So if the cannonball goes this way, we have to be prepared for the cannon to go this way. So the reason for the rope then is to prevent the cannon from like literally going all the way across your ship and then like crashing on the other side. Right? That would be it for again. Instead of putting a hole in the other guy's ship, you're putting a hole in your ship. I went to Boston to watch Patriots game, and I got a chance to go on one of the old US boats and stuff like that. I think I saw a cannon there. It was on like a rocker system, so that like it was built into like a track, and the cannon was on wheels. You've seen one of these before. And then the cannon would go up to the very, very front of like I suck at drawing, but like imagine this is like a track, and then you put the cannon on wheels. Right? And then as it shoots it this way, the cannon on its wheels would then slide backwards this way. You'd have like some sort of barrier for it. Okay, move on. Don't get too distracted. Okay, so here are the three things you guys need to be able to do. Okay. There's three types of collisions. So I've got some pictures in a little while, and we'll do the formulas for each in a second. First one is called a linear collision, where objects separate. Basically, I don't know, you hit your object. As I hit the object, I mean, I went this way, the object went this way, I backed off, right? Like, you envision this concept, right? Like, this applies really nicely to things like hockey, where like two different players body check each other, right? They crash into each other. Second possibility is the objects stick together. If you think hockey again, there might be a scenario where you hit a guy, but then like you both like fall to the ice in one big crumpled mess or something like that, where you don't really like bounce off each other, but like you hit each other and you like do that maybe. I've got a picture if you guys want to flip to the next couple of slides here of just some examples picture-wise of these. So this would be a good example of the linear collision where objects separate. You hit the one pool ball into the other pool ball and they're just like, you know what I mean? Whereas a car crash in the photo below it would be a good example. If you were to accidentally rear-end somebody and like your friend in the car crumples into the back of their car, really like they're stuck together. So that's the third one, the second one. The third one is the explosion example. So bullet goes this way, gun goes that way. Fair enough? So, on the slide I skipped, don't worry about looking back here, but on the slide I skipped are all the formulas that I need to work with. So these are the last ones, and they're in your book. If you guys have your data books, you know where to look for them. So these ones up here in the top corner. So my goal today is to work you guys through how to use these formulas. They're honestly quite straightforward. There's not a lot of tricks to them. Like I would say they're probably easier than these ones here, except you have to be familiar with how you're gonna have like little ones and twos next to everything. So I got those there. That's just to keep track of the fact that there's more than one thing crashing into each other. That's all right. So like 1 is for object 1 and 2 is for object 2. So let's try an example. So here's the first one. You've got a white billiard ball moving to the right, and it hits a black billiard ball at rest. Yeah. And then afterwards, I tell you some more information here. Long story short, maybe you better just draw a bit of a picture here, kind of visualize it. So you can draw like a drawing goes. I'm going to have a white billiard ball, so I'll just say this is white. And it's moving towards the right, and then it's going to hit a black ball. So that's the before picture. Right, B for before. B for before, and then A for after. Well, you guys think about it? I mean, logically, what's going to happen to the black ball? Black ball is going to stay over there, right? So the black ball, I might put it over here now, because the black ball, is still moving this way now, right? But sometimes when you hit like, especially a pool ball together, the white ball kind of keeps rolling forward. So I left a little bit of space because after the white ball crashes into the black one, the white one is also going to kind of keep moving forward. You guys visualize this? White and black. White hits black, and they both kind of keep going forward. Will they be going forward as fast as the original first guy started? No, right? Like they're just going to be slightly slower. So that's kind of what our goal here is. We want to figure out the velocity of the black billiard ball. So let me walk you through the way that I have to teach my grade 11 and 12 physics kids how to notate this. What I would do is I would call this guy, like this one would be say mass 1, and this one here might be say mass 2. So we just have to pick one of them to be 1 and 2. Well, in the after picture, isn't the white ball still going to have the same mass that it had before? Like it didn't change mass, right? And then this one would be mass 2 there as well. And then the other thing we'd have to deal with is we'd have to figure out like the velocities of each of them. So like this guy right here would have had a velocity 1. I'm going to use the arrow to indicate velocity 1. If that makes sense. Then this guy right here also has a velocity 2, only there is no arrow. What's his velocity? Yeah, so like if you wanted to, you could just say that it's 0 real quick, just remind yourself that it's 0. And then same thing afterwards. Afterwards, it's got to have a velocity, and that got to have a velocity. That makes sense? So you have to write it out 4 times. You have to write out mass of white, mass of black, and then later mass of white, mass of black. But really, it's not 4 numbers, it's just 2 numbers. So let's try the formula now. It's pretty straightforward. The formula is mass 1 times velocity 1 plus mass 2, velocity 2 equals mass 1, velocity 1 plus mass 2, velocity 2. It's kind of demo formula. So just using ends and b's everywhere. Essentially the concept is the first half of the equation is everything from the before scenario, and the second half of the equation is everything from the after scenario. That's all. So let's just start plugging in some numbers. Do we know the mass of the white ball? Yeah, it's 0.15, right? So I can make this one 0.15, and I can make the other mass one a little bit later in the equation, 0.15 as well. Okay. Then it actually says that the black billiard ball has the same mass. It's kind of sneaky. I hid it in there right there. It says the same mass. They don't have to have the same mass, but in this case they did. So I can make mass 2 be in both locations, also 0.15. Then we need velocity 1. What was the initial velocity of the white ball? It said it was 8 meters per second. So I'll make that 8. Then I need to throw in the number for V2. V2 would be the velocity of the white ball, which was 0, yeah. So I can times by 0. And then V1 is the velocity of the white ball again, but now it's the afterwards velocity, which was 2.5 meters per second. And then what we don't know is this V2 sitting way over here. Yeah, maybe don't you guys rewrite it. I'm just going to rewrite mine so it's a little bit nicer. What you're left with is 0.15 times 8 plus really nothing, right? Because that just becomes nothing. Equals 0.15 times 2.5 plus 0.15 times v squared. And all we have to do is just figure out how to bridge it how to get v squared by itself. Do you have any ideas? How do you get this v squared by itself? You're getting everything to one side and divide. You're both kind of right, just in different orders. So first I got to get rid of this stuff over here. How do I get rid of this stuff? Do I need to divide it or subtract it? Good, yeah. So whatever 0.15 times 2.5 is subtracted away. So like subtract 0.15 times 2.5, and that gets rid of that mess right there. And I think, Balka, you were ahead of me on that last step. Once you've done doing that, then divide by 0.15 right here. So then divide by 0.15 here, and that should give you that velocity itself. So I just think that just make sure you do the right order. Do the right steps in the right order. Don't do dividing before the subtracting. Grab my table. Yep. 0.15 times 8 minus 0.15 times 8, and then, oh, I have times 2.5. And then divide by 0.15. I got 5.5. Okay, so that's 5.5. What would the units for that be? Yeah, because it's the same units as everything else was. Did you get 5.5? Do it all in one big step here. Okay, what you should do is do the whole top part first, like all of the first little bit first, then press enter, then divide by 2.5. Because what your calculator interpreted as is you are only dividing the second part of the subtracting bit by 2.5, rather than the whole thing by 2.5. You got to think about that? Okay. 5.5 hopefully makes some logical sense. Because honestly, if this guy was 8, one of them's 2.5, the other one's 5.5. Shouldn't 8 be the same as 2.5 and 5.5? When you add them together, it's not logical. Now, the only reason why that's the same though is they all have the same mass. Because like, think about this. If you were to get rewritten by a semi, that kind of changes the math. If you are small and the semi is really big in terms of mass. So the only reason why that 8 equals 2.5 plus 5.5 bit works because the masses are all the same. It's kind of how you set up that question. That makes sense? Oh, let's try that one. Okay, the second type of question is involving a hitting and like sticking together type object. And so let me start by just writing out the formula here. You'll see that the difference here is it's M1 V1 plus M2 V2. It like starts literally the same way. But then afterwards, you gotta be careful with this bracket. It goes bracket M1 plus M2 V1 and 2. That's the formula here. Why is the second half of the formula change ever so slightly? They stick together, right? What does that mean? The mass has happened. Yeah, it combines, right? So can you guys see why you have to like go bracket M1 plus M2 because their masses have been combined? And then we don't actually have to write V out 2 different times because whatever that velocity is the velocity for both of them collectively. Because really what's happened is you have two things collide and then stick together, right? Body check fall over or something like that rather than body check bounce. So try the same thing here. If you don't need to draw a picture every time, don't worry about it. Like I only drew it for the very first one, but you probably can start just plugging in numbers. Like say, 2 balls at play, a blue one with a mass of 2.3. Well, I'll just pick one of the masses and make it 2.3. Pick one of the M's and make both of them 2.3. And then the red one is 5.6, so make that one 5.6 and that one 5.6. They hit each other and stick together. Here's the really important part. You have to make sure they hit the direction. If the blue one's moving to the right at 12, I can make this one be 12. That's fine. You see how the red one was moving to the left at 8.1? I need to times by negative 8.1. You know what I'm saying there? Because they're going opposite directions, you have to give opposite signs. What I tell my physics 30 kids to do is to just figure out which way is positive and negative. So like make right be positive and make left be negative. That's all. Right, just so you get your bearings. Sometimes you'll have to do like say up and down. It doesn't really matter who gets to be up or who gets to be down or who gets to be positive and negative. Just pick one to be positive, one to be negative, and just go with that for the rest of the question. Okay, well, the thing we were asked for is their final velocity, which is, rather than writing a little 1 plus 2, can I just write VF? Just to kind of make it easier. 1 plus 2 is going to be 1. I gotta go solve this. So, now this one is way easier to solve algebraically than the last one, actually, in terms of steps. Because really, the only thing you have to get rid of the VF is the 2.3 plus the 5.6. Just divide it up. You know what I do though? I would just add it together and find out what it is. Like 2.3 and 5.6 is 7.9. Really, which is the total mass of both of them, right? So all you gotta do is divide up to 7.9. So honestly, this is very similar to what the last question looked like. It's just make sure that you do all of the stuff on the top first, press enter, then divide by 7.9. And don't miss the negative sign, because they're going opposite directions. Let me know if you guys get this. Some of that. Okay, so we should talk about that for a little bit first. It doesn't have to be a nice even whole number, right? Like it was the first time because the masses were all the same as each other. But this time because the masses are different, that kind of affects the balance of the equation. So I wouldn't expect it to be just like, 5.5. That's just what I close it. Other thing is the negative kind of helps figure things out. What does that mean about the direction in which the two of them travel? No, they're stuck together still, right? It means that if you kind of imagine the hands of the pictures, one of them is going this way, and one of them is going this way. Two, hockey players are going to hit each other. Which way are they going to go after the collision? That way, because I made negative be that way. Right? The negative just tells you who wins the fight. Right? Like imagine you've got two crashing into each other, right? Possibility are they just hit each other and hope to stop. That could happen. More likely possibility, it goes like this and someone wins, or it goes like this and someone wins. So if you imagine these sports analogies, you've got a football or a rugby player and they go head on, right? Whoever has the more momentum ends up carrying the other person that way. Does that make sense? Like I think of like a running back in football, or I don't know what the position is in rugby, right? But they're about to get tackled. And if you can manage to have more momentum than the guy trying to tackle you, you might be able to force your way into the end zone kind of thing. If not, the defender wants to hit you with momentum and knock you backwards, right? Oh yeah, last one. This one right here is going to end up being our explosion one. And you can start by writing down the formula. So there it is. Okay. So this one's kind of backwards from the one we just did here. You're going to start with your masses, like M1 plus M2. The reason why is that the bullet is lodged in the gun when you start with. So rather than two objects coming together, you actually have two objects separating. So that's why the masses start off collectively. And then it's a V1 and 2. And then that'll equal M1 V1 plus M2 V2. Rather than do F here, why don't we do I? Because I would make more sense because this is your initial velocity. I don't really care what you use, like it doesn't really change it. So let's just start plugging stuff in, right? Mass of the bullet is 0.050. Mass of the gun is 5.0. This one can be 0.050. This one can be 5.0. The velocity of the bullet is 275 meters per second, and the bullet goes pretty fast, so that has to go with the small little 0.050 number. Here's where some kids, they get lost on this next step here. They'd say, well, I need to have V1 and 2 right here, and I need to know what V2 is. And they're like, which one do I leave blank? Well, we're gonna leave this one here, V2 blank. But then they might say, well, like, what the heck goes in this spot here? Because they didn't tell you what it was. What is the initial speed before you shoot the gun of the gun bullet? Yeah, that's the one that sometimes is implied. So that's actually a 0. It doesn't have to be a 0, but if it's not telling you anything, there's a good shot that it was at rest. I could be waving my gun around before I shoot it. No, but you could, right? More than likely it's stationary. Okay, what ends up happening on that one here then is that if this is then 0, really this whole side is 0. Yeah, so it ends up giving you 0 equals 0.050 times 275 plus 5 times V2. So it makes me know how to rearrange. So we've actually done one very similar to this before. You're going to have to divide by that 5, but not until you bring the 0.050 times 275 like to the other side by subtracting. So it'll give you negative 0.050 times 275, because now it's on the other side as a negative. Then you'll have to divide by the 5.0. Isn't this one over that about doing every single little step? Why would there need to be a negative on this? No, from a mathematical point of view, you're right, but from a real life point of view, there's the other reason. You're both right, for different contexts, right? From the math point of view, the negative is going to go to the other side. From the real life point of view, it's the bullet goes forward, the guy needs to go. That's it. 0.050 times 275 divided by 5. I got negative 2.75. So, okay. Yeah. So that's the recoil of the gun, like, I don't know, your hand or your shoulder or whatever happens when you shoot. That's it. Those are the 3 main formulas. So, I mean, hopefully you guys would agree with me. It's not actually, like it's, I don't want to say super easy or something like that, but it's not quite the same as the rest of the formulas here. Kind of see why I threw them in a different corner here, is that all it involves is like masses and velocities, and it's just a scenario sort of thing. Okay. The last thing we got to cover then, and I've only got just one last example here, is the remaining formulas that we didn't do. For the life of me, like I said, I don't know why I threw those ones in there. It must be physics 30. We got to talk about these ones here. So it's potential and kinetic energy. This eraser right here has potential energy because it's above the ground. As I let it go, it turns from potential. It turns from potential into kinetic energy. And it transfers from one to the other, right? The energy of waiting to move into the energy of motion. So there's the 2 formulas. You've done them before. Mass velocity squared. Do you know what G is? Do you know what the number is? If you guys are way ahead. Okay. Let's do our last example. This is my phone call.
Hello.
Hey. Where's Creighton? He was here. Apparently, no, he's not. I thought he was here today because I saw him during advisor time, but no. But he's, yeah. Okay.
Yeah, he's not in my room and he's not on my signed out board, so, okay, thanks. Have you guys seen Craig?
Brandon and Jason Creighton, can you please come to the office?
But not recently. Yeah, I just saw some earlier. Okay, this is basically what we're gonna do in our activity. So, probably like Tuesday. You guys care enough to make it on it beforehand, that's fine. If not, I'll just bring some random materials to use, like cartons and cushion, like padding or something like that. And the idea is you guys are going to put an egg in a plastic bag and we're gonna swing it into a wall. Okay. And we'll do it from like a short height at first, and then we'll build it up more and more and more and more and more until eventually it cracks your egg. And we'll see just how high we can build a helmet that the egg can survive. And as soon as the egg cracks, then you're out. Maybe I'll bring some chocolate bar for this does the best, so you have a little bit of motivation. Okay, let's talk about how we're gonna do the questions. These are gonna be the same questions that are on your lab, by the way. So use these as like your reference for what we do in the lab itself. First thing we're gonna do is calculate the gravitational potential energy. Okay. Well, gravitational potential energy is your mass times your gravity times your change in height. Maybe just save enough room for all of like A, B, C, D, a little bit of room for each. Well, we're gonna weigh your egg before we crash it into the wall. So I just made up a number here. I said it was 60 grams. We would have to make that kilograms though. So you have to divide by 1,000, which makes it 0.060 kilograms. One more zero. 0.060. Then you times by 9.81, because that's gravity. And then we just need to know the height that we're dropping. And so I said here we're going to drop it from a height of 8.50 meters. So 8.50, or 0.850. Sorry. 2.060 times by 9.81 times by 0.850. I basically got 0.5. Do you guys know what the energy unit is? I said yes. Do you know what it is? Nice. Yeah, joules. J for joules. Yeah. Yeah. So this is the energy unit for joules. Okay. So once we calculate just how high up, you know, like imagine your scenario, right? What we're gonna do is we're gonna take the egg from here, crash it into there. Probably won't break, right? From here, crash it into there. Did you get the announcement that you needed? Yeah. Okay. I didn't know where you were at. Because your name's on my board unless I'm totally blind. Were you here already, or were you just showing up for the first time? You were here? Can you make sure you put your name on my board for scenarios like this? Just because, yeah, we didn't know where you were. Okay. Egg crashing concept. So you've got your egg. From here, it probably won't break the egg, right? From here, it probably won't break the egg, but we'll take it to the point where it finally breaks the egg. And then that will be the first thing you do is we'll figure out how high each of you was able to make your egg get out from there. Whoever gets the highest, I guess. The next thing we're going to do then is we're going to say, well, all of your potential energy should get converted into kinetic energy. So we can actually use the kinetic energy formula for the second part, which is your kinetic energy is normally equal to 1/2 of mv squared. That's the formula. If all of your potential energy of height turns into kinetic, then we can actually solve for this velocity. Because what we'll do is we'll put the 0.5 joules as your kinetic energy. Then the mass of the egg was 0.060. And we need v squared. You guys see how I took the first formula to get energy? And I used the second formula, which is also energy, and I just kind of transferred one to the other. So, how do you get the v by itself? You'll have to square root, but that actually has to get done last. You'll have to divide by the 0.060, and you also have to get rid of the 1/2. I like to times by 2 to get rid of 1/2 myself. I find that's the easiest way of doing it. So if I times this by 2, that gets rid of the 1/2. If I divide by 0.060, it gets rid of the 0.060. And then square root. Mathematically, you guys must have heard the acronym bad math before, right? When you're doing algebra, you actually have to go in reverse order. So you have to do all of your add and subtract first, then your multiply and divide, and then do your exponents next. And because the squared is an exponent, you have to do your exponent last. So you actually have to go in reverse order. Anyways, take 3.5 we just calculated, times it by 2, divide by 0.060, and square root. I got 4.08 in here. 4.1. Whatever you round to, I don't really care. So velocity is like 4.08824. So you guys can envision this scenario. What we've now calculated, here's your wall, here's your egg in the wall. We now know how fast the egg is in the wall. Ideally, the way this should work is the higher up your egg managed to make it, the more velocity that the egg was able to withstand. You know what I'm saying? We now know the velocity at which your egg then broke. Okay. So then the question I have after that is,
Kevin Wells and Skylar Frank, please come to the office. Kevin Wells and Skylar Frank, please come to the office.
Well, momentum of the egg is just your basic momentum formula, which is like P equals M times V. So you want to go from here, just take your mass, which is that 0.060 again, and times by the velocity that we just calculated. So that number there. If you guys can, you know how like your calculator stores all the digits in there? Do you guys know how to reuse that number again so you're not like just do like answer? Like do answer times by 0.060, just so you're saving all the digits. So then this makes it 0.2449. That's how much momentum your egg has. The momentum units are probably kilogram meters per second. Next question I'll ask you is the deceleration of the egg, which is really acceleration, except it's going to be a deceleration number because it's going to be negative. The egg did slow down, right? It went from moving to crash. So we just need to use one of the acceleration numbers. We're going to use probably one of the ones up here. So see how it says acceleration is velocity minus velocity initial over time. Problem is that I don't actually have the time. So that one's actually not useful. I actually have to do a 2-step formula for this one. And there were a couple of questions on your quiz that involved like you have to use one formula and then use it to get the next one. On your quiz, those will be some of the last ones on your test. Those are the ones that we didn't quite talk about yet. Like 16, 17, 18, and 20. So in order to solve this, you're going to have to use the formula D equals VI plus VF over 2 times time. Are you looking for me, Brad? Yeah, sure. It's sitting in a pile on there if you want to grab it. So although we want acceleration, we don't actually have the information needed for acceleration. The acceleration is velocity final minus velocity initial. Well, we know the velocity final is going to be 0. We know the velocity initial because we just found a little out of it, but we're missing time. So we have to use this formula here to calculate time. And then the other number that I gave you here, back up to the original question here, say that says the block moved back 3 millimeters. Well, now that I know that as the thing crashed into the block just wavered a little bit, that gives me the distance then. Except the distance has to be in meters. So it'll look like this. 3 millimeters is 0.003. So 3 millimeters is in meters. And then, there's some numbers here. Velocity initial would have been like 4.0824. That should be enough. Velocity final was 0 divided by 2 to get time. So first we have to get time. 0.003. What did you do? You times by 2, and then you divide by 4.0824. I calculated the time, like 0.00147, give or take. That makes sense for time because how long does the crash of the egg actually take? I'm not talking about how long it takes the egg to swing down. I'm talking about the actual part of the collision, right? And that's actually very short. Right? That's the time that if you can lengthen it during a car crash, let's say you know what I mean? Like the amount of actual crashing impact. And so if you can lengthen the amount of time, usually by adding, like for your egg, you'll want to add more padding. If you add more padding, it lengthens the amount of time that it crashes for. Anyways, now that we have time though, we have to use it in the other formula again, which is that A equals V F minus VI over change in time. Now that we have that information, we can find the acceleration, which should be negative because it was slowing down. So it'll be 0 minus 0, 4 points. What's that velocity? 4.0824 divided by 0.00147. And to the best of your ability, try to use as many of those digits as you can. Like, try not to round it to like just 4 and like 0.15 or something like that. Try to use as many digits as possible when you're using like multiple calculations. 824 divided by that x over there. I got about negative 277. Yeah, that's right. Negative 2777. I guess if I round it, this becomes a 7. That would be meters per second squared, because that's the unit for acceleration. When it comes to the body, especially when it comes to like your car crashing and stuff like that, you don't want a lot of deceleration. The higher the deceleration, the less it leads to like concussions, because you know you guys know much about the brain concept, right? But like your brain is inside like a watery sac inside your skull, right? And Newton's first law will basically say that like things in motion stay in motion, therefore your brain is moving. Well, if you all of a sudden goes to a stop, but your brain keeps moving, boom, right? Like it causes that your brain to hit the front of your skull, or like when you like hit the back of your head backwards, it does essentially the thing where the brain sloshes around inside your head and like it leaves a bruise on your brain. So, anyways, the big deceleration number like that is not a good thing. Because if you're decelerating too fast, it means that the rest of your body probably isn't catching up. Okay, what's you guys have I don't. It wanted the time required for the collision. Yeah. So the nice thing about sometimes the way this one works here is that I kind of asked you the question in the wrong order, but we actually ended up solving it anyways. So we don't actually have to do E because we already found it. The last one, it wants us to find the force exerted during impact. And I'm going to show you guys how to calculate this force 2 different ways. So when I want to find force, there's actually 2 formulas for force. One of them is mass times acceleration. That's your basic force one, right? So it'll be 0.060 for mass times by that negative 2777. G7. That's pretty simple. I got a force of negative 166.7. What's it so negative? The egg hits the wall, but the wall also hits the egg, right? So that makes the law concept. So the negative, really what it's telling us is that the negative is how much the wall hits the egg back, right? Because it's not the egg that hits the wall that causes the egg damage. It's when the wall hits that egg that causes damage, right? The egg doesn't probably damage the wall. The wall damages the egg. Okay, other option. This is the formula that you guys were using yesterday on your one of your quizzes. I think it goes M bracket VF minus VI bracket over delta T. Yes. You have all that information. So you know how we got to the 166.7? This should give you the same thing twice. So 0.060 bracket. What was that velocity final? Velocity final is 0. Velocity initial was that 4.03824. And then the time was the 0.00147. I got the same thing. They have options. Anyways, that's gonna be our lab on like we do on Tuesday. So you guys, I'm gonna give you tomorrow as just time to get caught up. That's it. That's okay. You guys can use all the formulas on here. And kind of get the theory behind it. Yeah, in terms of stuff that you guys want to finish the first assignment? Yeah. So then we've got one more assignment. We've got the Hot Wheels lab that we were working on a while back. We're gonna do another egg crashing lab on Tuesday. Then we'll do a quiz on Monday and a unit test on Wednesday. That's kind of our. Don't procrastinate. And then when we start next week, the PS2, we will also you'll be here on Monday, but like she'll start doing sections with you guys on Thursday. And I'll still be in there. It's a good place to start.